Okay, so in section 4.5, we're going to be looking at optimization. This is going to be our other big story problem section for this chapter. Lots of fields, science, engineers, mathematics have something in common. We want to try to come up with solutions, especially optimizing those solutions. By optimizing, we're trying to make things most efficient, or if that's appropriate, and I often refer this to as min-maxing, literally minimizing and maximizing as appropriate. So I just already wrote in a couple ideas here for things that you want to minimize and maximize in real life. Like, for example, you want to maximize profit, minimize costs in a business. You might want to maximize velocity or talk about escape velocity, that kind of thing. Or in product design, for example, wanting to minimize surface area or maximize volume would be a couple other things that are commonly minimized and maximized. So in order to set up optimization problems, we need some sort of constraint, typically one or more equations that relates the variable and constrains the possible solutions in some way. Like, for example, if you're trying to maximize volume, I mean, you could go bigger and bigger and bigger if there wasn't a constraint, but the constraint might be that it needs to fit inside the building, for example, and so you have a maximum that it could be, or whatever that happens to be. So there has to be some kind of constraint to maximize something in most cases. Same thing for minimize. You could minimize, but then you can shrink something down to a point, down to 0, but you need to be able to make sure it can hold at least this much. So there's got to be some kind of constraint. And then we need to know what the objective is as well. So we're going to have a constraint function and an objective function. Putting this all together, we can set up an optimization problem that can be boiled down to the question of our goal here: what is the maximum or minimum value of the objective function subject to the given constraint functions? So we're going to be trying to optimize the objective function subject to our constraint. Let's take a look at the next page. It's going to have our procedures and guidelines for optimization. These are also summarized for you in the pink sheets of your notes, so you have that there as well. So guidelines for optimization, what we want to do is, of course, read the problem carefully, identify the variables, organize the information, sometimes drawing a picture. Then we're going to make sure that we write an objective function and a constraint or constraints functions. Those are also equations. There may be one or more. So the objective function is identified by being our goal. It's the thing that we want to optimize. Optimize is just general for max and min. You want to find the largest or the smallest. And then once I have those two things declared, the objective function, the constraint function, then we're going to use the constraints to eliminate all but one independent variable of the objective function. So the objective function usually has more than one independent variable until I take the constraints and break it down to having just one. So I get the objective function in terms of that single variable, and then we're going to find the interval of interest. This is similar to domain, but the difference is that we have to think about real world. So we're going to start there with domain for the interval of interest, but we want to keep that smaller by thinking about real world possible values for the variable in the problem. So oftentimes we throw out things like negatives. If you're talking about building a physical object, a negative side length isn't going to make sense, and so on. So making sure we keep that in terms of the real world possibilities. Then we're going to go into the derivatives. So we're going to find the first derivative of the functions so that we can get our first order critical values, and then we're going to test those critical values. Then in step 8, we're going to use some methods of calculus to determine whether it's an absolute max or an absolute min. We are looking for absolutes here, so absolute maximum or absolute min. And so you do need to make sure you check the endpoints as well, which is why that interval of interest is so important. It needs to be a closed interval of interest. Now, in step 8, there are 3 possible tests that we can use to classify these. We can use either the second derivative test or the test for absolute extrema, which was in the first section, or the first derivative test. So you're going to choose one of these, not use all 3 of them, of course, but choose one of those tests. And finally, once you're done, double check the problem and make sure you've answered all the questions. So let's take a look at the first example. We're going to label our steps here to make sure we get all of them. This one does say we can skip step 1, but we're going to label all the remaining steps. So this one begins with a pair of positive real numbers as a product of 9, where x is one of the numbers. I want to find the x value where the sum of the numbers is a minimum, and I already know the product is going to be 9. So There's no diagram to do here, so we're skipping step 1, obviously not skipping the reading, we need to read the question. And now we're going to write the objective and constraint functions. So step 2 is our objective, and step 3 is our constraint. So the objective function is the goal. It's the thing I want to optimize. So when I want to minimize or maximize something, that becomes the objective. And so my objective is a sum, and so if I have two numbers, I can call them x and y, and I want their sum to be a minimum. So I'm going to use s for sum equals x plus y, and that's my objective. Okay. Now, clearly that has too many variables. What I want to get it down to is a function s of x, perhaps, so that I have one independent variable. I have two right now, so we're going to change that with the constraint. So the next step, step 3, is writing a constraint function. That's where this product of 9 comes into play. So that's the product of the two numbers, so that means that x times y is 9. That's our constraint. And so now that I have my constraint function in step 4, I can use the constraint to get rid of a variable in the objective function. I want to keep x because x is my goal, so we're going to solve for y. So y is equal to 9 divided by x, just dividing both sides by x. And then plugging that into s, that gives us s equals x plus 9 divided by x, and so we can use function notation now and make this s of x equals x plus 9 divided by x. And so that's where we really have step 4 finished. It takes a couple steps to get there. So first we had to take the constraint and solve for a variable, then we had to plug that result into our s function to get into our s equation to get a function. There we go. So that's what I want in step 4. The goal for step 4 does have that word function because I should be in terms of a single variable, so I should be able to write it as a function. And now we have that. And then step 5, we're going to identify the interval of interest, or the effective domain here. Now, usually you have real-world constraints such as negatives not allowed for sides. In this one, it's specifically going to state that we need a pair of positive real numbers. So we're going to use that, positive real numbers, to help us out. And so I know that x needs to be greater than 0. I don't have an upper bound for it right now, so we will not be able to give it an upper bound. I can guess one later. If I need a closed interval for the extreme value test, I could try for that. Since I don't have a closed interval at the moment, I'm not going to be able to use the extreme value test, so I will just use a different test, like the second derivative test or the first derivative test. So we'll leave that right now as our interval of interest. Now, the next step, step 6, is going to be finding the first derivative. So s prime of x is 1 minus 9 times x to the negative 2, or 1 minus 9 over x squared. Since this is x to the negative 1 power, I have negative 1 times x to the negative 2, and the 9 stays as a coefficient. Okay. Then step 7 is finding the first order critical values. So in step 7, we're going to both look for places where the first derivative is equal to 0 and look for places where the first derivative fails to exist. Okay. So first derivative equals 0, 1 minus 9 over x squared equals 0. If I add that to the other side, 1 equals 9 over x squared, so x squared equals 9, and x equals positive and negative 3. And then fails to exist, that would be denominator equals 0, so that's x squared equals 0, so x equals 0. So this derivative has 3 first order critical values, but I only care about one of them because only one of them is in the interval of interest. The interval of interest, again, being positive only, x greater than 0. So we're going to say that x equals 3 is the critical value. Oops. the critical value in the interval of interest. In the interval of interest. Okay, so there are 3 critical values. We'll make that note as well, because depending on which test we use, we may need that knowledge. So these are all critical values. Okay, now on to step 8, picking a test. Okay, so I want to discuss that real briefly. We have those 3 choices. Again, we can use the first derivative test, the second derivative test, or the test for absolute extrema. I can only use the test for absolute extrema if I have a closed interval, and I don't at the moment have a closed interval, so I can't use that test. So I'm not going to use the test for absolute extrema in this case. Instead, we're going to use the first derivative or second derivative test. Okay, the first derivative test is that table form, and so the second derivative test will probably be a little more efficient right here, because I can use just the one critical value that I'm interested in instead of having to do tables for all of the values and do the whole thing. If I only had one critical value, maybe I'd go into table form. Remember, there are also some cases where the second derivative test doesn't apply, and that's going to be the case if my second derivative is equal to 0. So let's start with the second derivative test, which means I'm going to find the second derivative, which would be, since I have 1 minus 9x to the negative 2 as the first derivative, it's going to be 18x to the negative 3 for the second derivative, and then we evaluate the second derivative at our critical value, so at 3. And so it's 18 divided by 27. It doesn't matter what the number is, it just matters that it's a positive value. And so remember that that's a positive value, which means that at your critical value, you are concave up, and so if you're concave up, you can draw the conclusion that x equals 3 gives a minimum. Okay, now luckily minimum is what we are looking for. Don't forget, back to the objective, we're trying to minimize the function, so it looks like we have done that. So we can now conclude that x equals 3 gives us a minimum, and we can find the y value as well. Since I know that y is equal to 9 divided by x, y is going to be 3 as well. So in step 9, we can finish off those details. 9 divided by 3 is 3, so we can conclude that if x equals 3 and y equals 3, the sum is a minimum. So the product is 9 and the sum is a minimum. All right. Now, this question was a very good introductory question, but it was pretty abstract. We weren't talking about a real situation. We're talking about just 2 numbers and their sum and product, but it gives us an idea of what these kind of questions will look like and what we can see moving forward.